As the quiz is coming back, let me tell you what we're going to do in the remaining part of the course, because one person asked me about this. All right, we're going to cover radar thoroughly today. We're going to go through the Doppler shift and actually go through some things that aren't in the book, but I'll give you supplemental problems and make it clear to you. Then we're going to go into electromagnetic compatibility and interference in the next chapter. Now, the reason I'm going to talk to you just for a second about this while these quizzes are going around is in the real world, where profit is the bottom line in companies in this country, a lot of times products are designed, they get a prototype, they're fabricated and everything, and they're about to go out the door, and something unforeseen comes up. For instance, there may be a problem in the field of them being unable to pass real lightning tests. In other words, lightning itself may be something that they thought they accounted for, but they didn't really. The people that end up trying to get the product out the door at a reasonable cost are called compliance engineers. They could be called other things too, but it's what they really are. And they're people that are experts in electromagnetic compatibility and interference. That means they know FCC law. The law allows certain amounts of radiated emissions over the spectrum. It can't be above that. Certain amounts of emission into the wall. If you ever plug something in and you think that it's just 60 hertz and power coming your way, you're wrong. There's any of the high frequency stuff up from anything from 10 kilohertz up, from like digital clocks and stuff, that some of that goes back into the wall, and that affects everything that's on the other side of these plugs. There's laws for how much you can transmit back into there, and when you build a product, it can't be susceptible to this if it's built in this country within a margin of error. Those are the people that are very, very valuable once you get good at it, because they can take something that's not working, it looks like it's a $10 million fix or a $1 billion fix in some cases, and they can make it work at a price that's very reasonable by adding one or two components. So that's what a compliance engineer really does. But they're also, from what I can tell, the highest paid people. Let me finish my thought here on this one. So why I'm saying that is because I teach EMC, it's electromagnetic compatibility. This fall, there wasn't enough people in it, and I was curious about that, and I'm thinking, I want to make sure you know what they do. I mean, if you're not interested, don't take it, for heaven's sakes, but they take everything. It's electronics, it's Emag, it's signal processing, it's the whole 9 yards. You're basically not just the jack of all trades, you become basically very knowledgeable about how all trades affect your products. Adtran is a company I know about, and Dianetics, that they have some, well, at least at Adtran, they have some of the top end people at compliance before they shove product out the door. And anytime you're marketing a product that has to meet FCC laws in this country, in CISPRI in Europe, and there's other governing bodies, and if you would ever have a product to the military, it's called military specs. Have you ever heard this term? Military specs are by far the most difficult to meet, because hospitals are bad, but military specs, they're asking next to the impossible. But the reason they are is because if anything goes wrong, I mean, bombs go off and stuff. So they have the highest threshold to pass. I'm telling you this, if you get a chance, you don't have to take my course or anything like that. Read about it and think about it, because those are the people that do everything you can imagine. And they're usually, I can't say with authority, but most of them are super bright to begin with. You don't get into this racket, that racket, unless you're really somebody who's, you might say, has got a knack for it. You're just kind of born with the ability. It's like a concert pianist. I don't care how much you practice. I don't care how much I practice playing piano or trying to be a fine artist. I'm not going to be one. You have to be born with some of that stuff, and I'm not. Anyway, now getting back to this quiz, I want to go through it with you because both quizzes are fundamentally the same. We had an antenna. I'm just going to call it a transmitting antenna. It has the gain of the transmitter, and it had an antenna impedance. I'll call it Z of the transmitter. Here, that's one end. On the other end, you had a receiving antenna. It had the gain of the receiving antenna, and it had Z of the receiving antenna. Now, the way we actually get what we need over here, we actually want the power transmitted. That's the power transmitted. Is what we want, or call it radiated. How's that? Power radiated. Well, to get that, we draw an equivalent circuit where we have a voltage Vs, and then we have an antenna impedance, Z antenna. And the steps are this. And I thought I went through this systematically in the class, but I think there was a problem. So I'm going to go through it again and make sure everybody understands. Does everybody understand what I'm doing here? This is representing that antenna plugged into the source voltage, all right? It's at a given frequency. I think it was 8 gigahertz. Now, the first thing we're going to get is this. That's the antenna and current. And this would be at the source. And that's simply going to be equal to Vs over Z antenna. That's it. As a matter of fact, I like to put a magnitude there so people don't include phase and accidentally mess something up. All right, just the magnitude of the antenna current. Got it? Now, after that, where are the tests right now? I mean, quizzes? Okay. You're in luck. You can still get yours. So once I have this Z antenna right here, it actually has a real part, and I'll call that R-rad. It's the radiation resistance antenna, plus J some X of the antenna, of the transmitter. That's really the imaginary part. Now, on one of them, it was like 80 plus J20. On the other one, it was 73.2 plus J42.5. The only difference in the quizzes is I switched the antennas. That's it. Right? And I switched I think the power source, the voltage on one was 100. The voltage source on another was 50. I put the solutions to the quizzes up on OneNote. So both of them should be there if you look. And I think you're looking. Or aren't you? No. Are you on OneNote? Okay, they're on there. So you won't have any problem. But I want to go through this. And if there's a question, ask it. So after I have this, the next thing I'm going to get is P radiated. So P radiated is going to be simply 1/2 times the magnitude of the source current squared, and then it's times the radiation resistance. That's the radiated power. You have to know how to get that. All right, so the key was getting the current. From the current, you get the power. Now that you have the power, the next thing you're going to get is the power density on this. And I'll call this P av. All right, just P av. So P av here, the average power density in watts per meter squared. I always tell people start with the total radiated power and divide it by 4 pi r squared. Now you know that's the power density without any effects of gain, any sharpening. The gain of the transmitter focuses the power. So you put the gain of the transmitter there. Now that's the power density at the target, or in this case at the second antenna. Make sure you follow me on this. Because I'm going to ask you. I'll ask you to reverse engineer it. I'll say if the load gets so much, how much was sent? Follow me? You have to understand all portions of this to work this problem well. Because I'm going to ask this problem again. I got too big of a discrepancy. This should have been an easy one. All right. Now, after I have that, that's in watts per meter squared. Right? There's two answers. So now I have the power density on the second antenna. Now I have to find the total power received by the second antenna, P received. So that amounts to taking the power density right there, that's P av, right? And multiplying it by the effective area or aperture of that second antenna. Follow me, class? How big it is electrically. Well, how big is it electrically? It's always lambda squared over 4 pi times the gain of the transmitter, whatever your transmitter, receiver, gain of the receiver. So now I have the power received. This is the way it should have worked out sequentially. These are how I ask these questions. Everybody got that? All right? Now, once you have that, the next thing you do, and I try to follow your thoughts on this. Sometimes I had one guy put down a waveguide equation. When people are just throwing stuff out, you get no credit. It has to be logically shown to me what you're thinking so I can give you any kind of partial credit. So once I have this right here, now the next thing I'm going to do is draw the circuit where I have effectively, we talked about this, there's an open circuit voltage that's going to be used to find out the actual amount of voltage that's at the load. Right? And then this has some Z of the receiving antenna here in series with it. That's internal. And then there's the load. I think the load in both cases was 50 ohms. That's RL. And there's going to be a voltage across the load. Right? So V open circuit, and we proved this, we said the way we get this, you could say it's a fictitious V open circuit, but the way we get it is say that this power received is the power that's received by the antenna, but we can't use it all. At most, we can use half of this, right? All right, because even if we have a matched antenna, half the power is going to be re-radiated or scattered again. Follow me in this class? So the way we get the V open circuit is, well, I'm not going to go ahead and draw that whole thing out, but we can say that V open circuit is equal to the square root of 4, right? And then it's times the radiation resistance, R rad, of the receiving antenna. And put receiving here. And then it's times P received. So that's it. This P received goes in here, right? And that's going to be a value. Now, you don't need to worry about angle in any of this stuff. I'm trying to really make sure I hit this one hard. Here, the radiated power, you don't put the angle in it. Got me? You don't care about that. Here, you don't care about any angle, anything like that. That's V open circuit, right? Now, once you have V open circuit here, to get VL, it's straightforward. I can say VL is just V open circuit, and then it's times RL over RL plus, and then it would be Z antenna, or Z receiving antenna. And do yourself a favor, put a magnitude there, because that's the only thing I care about. I don't want a phase. It doesn't do me any good in the real world. Now that's the voltage on the load. Power on the load is pretty straightforward. That's a resistor. You could say that now that's the voltage on the load. The power at the load can be equal to either 1/2 times the magnitude of the load voltage squared over the resistance, that's 1. Or you could take 1/2 the magnitude of the load current squared times R, right? Either one of those two will do it. Or you could have 1/2 times magnitude of VL times magnitude of IL. And what is IL? Well, it's this current, right? And IL can be just VL over R. You can do it a magnitude. You all follow me? So it doesn't matter which one of these things you use. This is the process you go by, all right? And there was a lot of people that, at least from what I could tell, they didn't know how to get the power received correctly at all. And from there, they didn't know how to get the open circuit voltage. Okay, so make sure if you made mistakes, you find out where they are and make sure you can remedy those mistakes, because you're going to see this again. And I'm going to throw something at you. Yes, sir.
Sorry.
If it's a specific question about yours, see me afterwards.
That was just for this problem.
Go ahead.
Why did we not use PREC equals G1 GR, G transmit GR times lambda over 4R squared?
You're talking about the Friese equation, you can do it that way. But the reason I'm doing it this way is because I asked for things that aren't in Friese. I'm asking for the incident power density on the second antenna. That's not there. And that's the real reason I want to make sure you can do it this way. You can do that. That'll give you the right answer for P received. All right? It's absolutely right, and you can get the right V open circuit. But that will not give you the power density that I asked for and on the second antenna. Everybody got that? Now go over your stuff and find out where you made errors and clear it up, because I don't want to see any kind of problem with this. This is real important, because we're going to radar next. I was already talking about radar. Radar relies on your understanding of this. So I'm going to do radar. I did it one time. I didn't give you any homework on radar. I'm going to this time, and I'm going to give you homework that's beyond what Wentworth's book has in it. And I want to make sure we're clear about this. Are there any questions about this? You can just run the numbers on your own, but they work out to the solutions I posted on MathKid. Has anybody tried MathKid in here since I've talked about? Anybody? 1 and a 2? It's worth it. I'm telling you. You don't need him on quizzes. What you need to do is run through a whole bunch of problems. This will actually help you solve problems fairly quickly, because the mathematics you can do really quick on MathCAD. I'm telling you this. I've used MATLAB. MATLAB is not what you see is what you get. You have to go ahead and rerun it every time. And in this one, if I change one thing at the very top, everything changes sequentially. I'm pitching this. I don't get paid to do this. I don't have stock in this company, but I realize as a student, I would want to use this if I were where you're at, because I can fly through homework with this. I can do I can probably do every problem in the back of Wentworth's book in this chapter in less than 2 hours. And I mean, with MathCAD, knowing how to use it. I can't do that on my calculator, I can assure you that. Just the number of punching in stuff takes forever. Okay, now, no other questions about this? Now we're going to go through radar again and make sure everybody has this down. We're going to go through the basic radar range equation. Then we're going to do the Doppler shift. And then you're going to find out about range. Yeah. Why? Is there something I don't know about happening? When to what? Get up? Oh, well, let's assume we're having one then. You work all night or something? I had a kid, I don't know if I ever told you guys this. This is one of the weirdest things ever happened, and I never was prepared for it. I had a kid, and came into an 8 o'clock class. Did I tell you this or not? Oh, God. So this kid came in every day, and 5 minutes into the lecture, he sat right up front. Didn't matter how loud I talked or anything, 5 minutes into it, like clockwork, he was out cold. He was asleep. I thought he was dead once. And I had people nudge him. I mean, you can have people with diabetic comas and everything. You don't know what's wrong with them. I nudged him a few times. He's alive. Just let me sleep, okay? So let him sleep. Well, I start calling him Captain Narcolepsy. And I mean, I address this trying to make fun of him to get him to at least be attentive. This guy worked all night and drove here, right? The sad part was, and this is why I don't encourage people to work all night and come to class, is he was driving here one day and he fell asleep at the wheel and was in a horrible wreck. And I never did see that kid again. I don't know what happened to him. That's a true story. So when I see people passed out, I don't always assume they're just tired. Sometimes I think there was a bigger problem, but I'll never forget that. All right. You'll probably hear from this kid at some point now that I think about if he's alive. How not to live your college life. Anyway, now we're going to go ahead and do this. This is the gain of a transmitter, and I'm going to assume that we can figure out how much power, I'll call it P rad here, is radiated through that antenna. Now, it's radiating power out here. This is a standard radar. All right, and I have a target out here. Now, this is the target. That's what we're looking for. The target is going to be at a distance r. It's the radial range, and you always have to get the radial distance to the target when you're talking about a radar problem. Let's see if this one works a little better. Yeah, this one does work a little better. The target has something called a radar cross-section, or RCS. The symbol used is sigma. I don't like it, but it's used everywhere. Radar cross-section is in either meters squared, or sometimes they take the log of it, and you'll see dB meters squared, or dB square meters, SM. Now, let me give you an example of this so you don't get messed up. If you see a radar cross-section of 10 meters squared, that would translate into 10 times the log of 10 dB meters squared. Well, what's the log of 10? Base 10? 1. So it would be 10 dB square meters. This is typical. All right, this is typical. So the thing is, what you have to understand is sigma linear translates, that's in meters squared, to 10 times the log of sigma into dB square meter. You just have to understand this is a common thing done with radar. They list things in terms of dB square meter, frankly because of the enormity and differences in size, target size. Planes can have areas that are about 5 to 10 meters squared, cross sections looking straight at them. All right, incoming missiles and stuff like this, if they have stealth tips less than 0.1 meters squared, and all the way up to the really big planes or blimps and stuff where they're literally hundreds of meters squared. So you got to understand there's orders and orders of magnitude, and that's why we bring in dB. That's the one reason, because it's easier to deal with. Then I've got this target. Now the radar signal comes out, it hits there, and then it scatters in all directions. Some of it is scattering back here, and then there's power received back here, call it P received. Remember that P received is not the power you can actually use. You can only use 1/2 of that at most. But just remember, this is the general flow. So the way we figure out the amount of power received, if a certain amount of power is transmitted, is you go through it step by step, just like I did with the Friis transmission equation. First thing you say, if I have total radiated power, and I divide it by 4 pi r squared, now that's how much power density would be coming from this transmitting antenna everywhere, right, without any sharpening. The next thing you do is multiply by the gain of the transmitter, the transmitting antenna. And it's the gain of the transmitting antenna in the directional gain at the target. So if you have something where you got a bore sight gain of 30 dB, but you're off target by 30 degrees or 40 degrees, and the bore sight gains down to a 10 dB or something, you have to use the 10 dB. Do you follow me? It's not always the maximum gain. It's the gain in the direction of the target. And I'll talk about that more when problems are given. All right, that's the power density. Do you all agree with that? At the target, correct? Now, the target, the bigger the target, the more of this is reflected. So then we take this and multiply it by sigma. Now, that's the amount of power that's intercepted by the target and re-reflected. Does that make sense to everybody? This accounts for isotropic scattering in all directions. Really what it is the amount of power that will be reflected back in the direction of the incoming signal. Follow me on this? All right, so that's power is being re-reflected. Now that falls off as 1 over 4 pi r squared again. That's how power falls off as it's radiating. Follow me on this, class? That power is radiating back here, and then it hits this antenna. So we have to see the area intersected, the antenna area, but it doesn't have to be the transmitting. You could say it's the gain of the receiving antenna. That way you can cover your tracks in case there are two different antennas. So now we go ahead and we make it, how electrically large is that antenna? Y'all remember this, class? What is it? Lambda squared over 4 pi times the gain of the transmitter. Receiver, pardon me. Gain of the receiver, that's in the direction of the target. Clear on this? Now that's how much power is received back at the transmitting antenna. And this is a monostatic radar. It means the transmitter and receiver at the same locale. In general, that's true. From 99.9% of all radars you're ever going to deal with, it's true. However, in the military especially, they have they have bistatic radars, and the reason that they do this is because they want to, with stealth technology, this kind of radar is, from what I've been told, basically ineffective for anything that's they've designed with stealth. Now stealth, there's two things you have to understand about stealth. The very first generation, do y'all remember the F-117? The first generation fighters had sharp, clean edges, but they reflected all the power away from the signal incoming to it. They're designed to do that. And you could basically take that plane at any aspect, this is a rather remarkable design, and blast it and would reflect all the energy, radar energy, away from the direction it came. Very little. It had the radar cross-section. You can look this up at, I think, at whatever the target acquisition radars were at that time, probably about 10 gigahertz of less than a seagull. So they're very small. It's just for the record, all right, it's almost impossible to see a seagull with a radar if it's more than about 60 or 70 yards away with a police band radar. They're pretty good at short range. You can't see them. When you're talking about something the size of a seagull, 10,000 feet in the air, 20,000, you're not going to see that. Not even with the best radars, all right? Not with monostatic. But with bistatic you can, and here's why. Because some of that reflected energy is going to be reflected at an angle off that's going to hit the Earth. So bistatic radar is the same as this, only, and I'll go through that, you're going to have basically a transmitting antenna, and then your receiving antenna is going to be somewhere else. And you're looking for, and you won't just have one a lot of times. They'll have a whole array. And this is a very complicated antenna system because timing is essential. You don't understand how tough it is to time all that stuff when it's miles and miles away from each other. But this equation right here is the basic equation. It's called the radar range equation that gives you the power received. Now that's the form I'm showing you. In general, the way it's given for a pure monostatic radar is this. They say P received over P transmitted, or P radiated in this case, will be equal to gain of the transmitter, gain of the receiver, times the radar cross-section, times lambda squared, and then they'll go ahead and put 4 pi here and cube it. They'll take r to the 4th here, and that's the fundamental radar range equation that gives you, I call it the goodness. It's a figure of merit for the radar's performance for a certain target. Now this is going to be small. 10 to the minus 7, 10 to the minus 8, 10 to the minus 11 kind of deal. There's all sorts of things that happen here with radar, but this is the basic radar range equation that you have to know. Follow me? Do you remember me going through this? Make sure you can go through all steps, because I'll ask how much power is on target. I'll ask how much what's the power density reflected back to here. You need to know all of it. Now the other aspect, and this is very basic radar at this point, it's the simplest type of thing. The second thing you need to know is the Doppler shifts involved. Y'all know what Doppler is. You can hear Doppler shift with automobile engines, right? You ever been to a race car, any close track race? When they're coming at you, you hear when they're going away. It's a Doppler shift, and actually the engine didn't change revs. What you're listening to is a Doppler shift. So it's apparently something that's lower frequency when it moves past you, higher frequency when it's coming at you. Just remember that. So Doppler shift when a target's approaching is always higher, and Doppler shift when it's leaving is always lower. But the Doppler shift shifts the actual apparent position of the recovered signal. That's the key thing. Remember, when you're listening, you're hearing something, right? If the thing wasn't moving, you would just hear the RPMs of the engine, basically. But if it's moving, then you have that additional shift called a Doppler shift. So how do we get Doppler shift? And I'm going to take that off and do it. Now, there's a Doppler shift that includes possible relativistic changes. I'm not going to do that one. I want you to be aware of it for one reason. Some of you probably are going to be working with things that involve satellites at some point. NASA and some of the other, I mean, the amount of activity right now for spaceborne stuff is pretty high. So if you start working with things that are in space, either orbiting, low Earth orbit, or beyond, you're going to have to use the relativistic form. I can give that to you, but first I'm going to start with the non-relativistic form. That means things aren't moving close to the speed of light. They're really, in truth, almost everything is not moving close to the speed of light. The problem is, when you're dealing with anything that has to do with NASA and stuff like this, there are things out there that do have velocities that start getting close to like half the speed of light. You have to be aware of it, at least. All right? There's a lot of weird stuff. If you can read about some of the weird projects they got, but I don't even know about how to quantify some of this stuff. You know what do you know what the solar wind is? It's just charged particles, right? Yeah, but it's I don't even know because it's helium hydrogen decaying. You're getting the solar wind is basically charged particles that are moving, but they're fairly massive. The thing about it is when these things near the surface of the sun, because of all these magnetic fields, there's accelerations and there's velocities that get like half the speed of light in some of these eruptions. Just be aware of that. I don't know if you're going to have to worry about it, but be aware of it. All right, so now when we talk about Doppler shift, this is the way it works. We know if I send out a signal and hits a target, comes back, the actual signal travels 2R. Do you all follow me? If you have a transmitting antenna right here with a certain gain transmitter, and it sends a signal out and it hits this target with a certain RCS, and this target is a distance R away, well, for the signal to hit it and come back, the total trip is 2R. Do you all agree with that? Now, 2R, that distance is something that's important. We know that the time it would take to get from here to here and back to here if we're moving at the speed of light, I know that this distance is really c times the actual delta t it took to get there. Do you follow me? Everybody? So we can see what delta t would be. Delta t would be equal to 2R divided by c. That's the first thing. That should make sense to you. There should be nothing hard about that part. Now, we moved out 2R, and instead of delta t, I want to figure out how many wavelengths are there. Please just listen to the reasoning behind this. Well, if I divide that by wavelength, which means now I have to know the transmitting antenna's frequency of operation so I can get the wavelength equal to C over F naught. Do you all follow me on this? Now, this would be the number of wavelengths I am away. All right? Has nothing to do with meters or anything like this. Wavelengths, right? The wavelength itself could be a meter, it could be a tenth of a meter, it could be a micrometer. But this is how far it is in wavelengths for the actual, how far the transmitter is from the target. Do you all follow me on this, class? Now, if I take this right here and I multiply it by 2 pi, now I get the number of radians, because each wavelength is 2 pi radians, right? You'll see why I'm doing this. Do you follow me? So that would be the phase, the total amount of phase change the wave would have from the time it's transmitted times the time it's received. Can you appreciate that? We could do it in terms of delta t, right here. That's the time difference. This is the phase difference. Now, this phase right here is interesting, because if I take the derivative of phase with respect to time, I want you to see what's happening here. I didn't mention this. This target is going to have a component of velocity in the direction of the actual antenna that's transmitting. It's called VR. It's called the radial velocity. It can be coming at or going away, but there's a component of its total velocity in the direction of the antenna. Do you follow me? Everybody? So if I think about this, as time goes by, there's a change in both distance, right, if that plane's flying at it, and phase. Does that make sense? And your total trip time is going to change too. But we can estimate how fast it changes by saying, if we take the derivative of this with respect to time, that's the derivative of phase with respect to time, here we would get 4 pi over lambda times dr dt, right? Now, what do you think I'm going to do with dr dt? That is velocity, right? It's the rate of change of the position of the target with respect to time, but it's the rate of change in the direction of the target. That's important. Not the total velocity change, it's the velocity change in the direction of the target. So now I can say this right here, I'll put it up here. I can say d phi dt is really equal to omega d, because that's in radians now per second, right? When I take a derivative of radians in terms of time, I get radians per second. And that's equal to 4 pi over lambda times, and you might as well just put it in the radial velocity, v sub r. Can everybody follow me on what I'm talking about here? Now, that isn't the thing that we use, WD. We know that omega, or omega d, is really 2 pi, right? 2 pi times fd, where fd is the Doppler frequency. So you can see if I take 2 pi and divide it into that, I really have what? 2 over lambda VR is fd. And write this down. This is the Doppler frequency. F sub d. And Whitworth, huh? Yeah, this is F sub d. It just means the d is Doppler. That's all it is. So F Doppler is going to be equal to simply 2 over lambda times VR, and that's it. But it has to be the component of velocity in the direction of the target, and that's the Doppler shift. Now, when I say the Doppler shift, what does it mean? Here's what it really means. If we transmit a signal and we look in the spectral domain, and let's just take a look out here, and this is going to be the apparent return in power. Call it P received right here. What you're going to see is there's going to be just, there's going to be noise here. And then where the target is, if it's not moving, you're going to see this. You're going to see basically something like this, where this would be P received of the target that you get from that first equation I put up there. It's an estimate. Do you follow me? There's noise always on these things. This is what's called a spectral analyzer, or a network analyzer in some cases. You've seen this, haven't you? On this axis, I'm sweeping frequency. And it does this. Now this, if the target is stationary, is at F naught. If the Doppler shift is something, if the target's coming at us, then the Doppler shift will shift that whole profile, whatever it is, up to F naught plus FD. and you would have this then. So it would shift this way. And if F Doppler, or if the target was moving away, then this would shift this way to F naught minus F Doppler. And it would literally take this and just shift it to here, and this and shift it to here. Your instincts tell you there's some minimum threshold for what I can see. You have to shift so much, because this is not an absolute spike. This has actually got some finite width to it. It's a profile. And that's something we get to in radar. I go into great detail about that. You know, what level, how fast you have to be going before there is an apparent Doppler shift that's visible on a radar. There's all sorts of things that I could get into here. I'm only going to get into the things I think are most important for this class. Does everybody follow me on this one so far? For Doppler shift? We'll do a problem with all this stuff in it. But there's two last things I want to go over, and then we'll do some problems. One is going to be the range resolution, or I should say maximum non-ambiguous range, and the second is the range resolution, or how far apart can you see two targets, and notice that they're distinctly different targets. And I'll explain what I mean by both. So we have this. Now I got to show you exactly how a radar signal, the actual voltage that's going to be feeding, or I should say voltage or power that's going to be feeding the transmitting antenna, what it looks like. So listen up, and you don't have to write this down. I want you to just listen. What you normally have is this. If this is time, what we have is something called the baseband signal. This is not going to be modulated, or this is something that will be modulated. This is of the order of kilohertz. And what it looks like is this. It shows you the voltage at the antenna, or I should say the voltage that's going to drive the power amplifier. And it's going to be some voltage V naught, and it comes over, and then it goes to 0, and then it repeats. All right. Now, and it keeps going on. This is how radar pulses work. And it's going to keep going on and on out to n pulses. For now, they can assume an infinite number. Now, this has a certain on time, tau. And it has a certain period, t. This is actually called a pulse repetition interval. But you don't have to worry about the details of that. Now, they take this waveform and they multiply it by the high frequency cosine waveform at the frequency you're going to transmit, 10 gigahertz, whatever. So actually, what it looks like is this. You got about maybe 10,000, maybe 100,000 different cycles, and then dead time. Make sense to everybody? Now listen to me carefully, and I'll explain something. When this transmits, just think about it. It starts transmitting. Then it hits a signal, or it hits a target, and it reflects back, right? If the reflected signal came back in this time frame, we wouldn't know if this pulse sent it or if this pulse. That's ambiguous. Do you follow me? So for a standard radar, there's something called the maximum non-ambiguous range. And this is just R, they call it RU. It's maximum non-ambiguous range. Non-ambiguous range. R sub U. And the way they get that is this. Well, listen. The total amount of time right here, t, right, in that time, what has to happen? The pulse has to go out, strike the target, and return before that time's over, right? So we know that time times c is actually equal to 2r, don't we, class? Do you follow me? Now, that r is given a special name. It's RU. So you can see the maximum non-ambiguous range right there is going to be given by the actual t, the period, or the pulse repetition interval. I'm going to use t because you're used to seeing that as period. It's t times c divided by 2. And that's the maximum non-ambiguous range. Now, some people are going to say, but you know, what if there is a target out there when this is transmitting, right? Here's the way this works. There's a lot of orders of radar development. Usually by that time, everybody knows the size of the targets they're looking for. And they know one thing. They know the threshold of what they can see with the return signal. Just listen to me now. So they know they can see something that's got a return power of 10 to the minus 10th watts per meter squared, or just watts total, all right? But they can't see something that's 10 to the minus 15th watts. So what they do is this, usually. When they figure out the size of the target and all that, right at this range right here, they know if there is a target past that range, the received signal from that target would be in the noise. They wouldn't see it anyway. That's sort of the game they play, all right? Now, admittedly, that's not really true because targets could easily pop up that are much larger. There's a lot of other things, but this is a first order working thing. And I'll tell you one other thing about this. There's so much work in this right now. One other way, have you had match filters yet? Have you had anything with correlation yet? You're going to get this. When you have that, you're going to find out if we have this signal and we make, not the transmitting frequency, we make this actual envelope there something unique. Something unique and easily changed from waveform to waveform. Then when we get the return signal and we get rid of the high frequency, we can do something called correlation or use a match filter, and we can actually see what pulse is associated with the return pulse. Now that's a much more complicated problem I don't have time to get into because it requires a lot of memory. But that's what we're doing also. And there's all sorts of tricks. Radar is filled with trickery, filled with things you can do to pull signal from noise. But this is the maximum non-ambiguous range. There's a second thing that you always want to know with radar. And it's not just military. Anything that has to do with organizing aircraft landing, they want to be able to resolve more than one target, and they want to do it at a short range. For instance, if my wallet and my phone here were two targets, well, could I resolve them, say in distance this way? If they're flying at slightly different altitudes, there's going to be some minimum threshold that I can resolve. And beyond that point, they'll look like one. And where you really see this used to hide numbers is, have you ever seen planes fly in formation? All right, one reason they do that is they don't know how many planes are out there. If you're a radar operator, when I was on the carrier Eisenhower, they had World War II radars. These are legacy radars, and still used. They're not bad radars in terms of long-range navigation. But if you looked out there, there could be the whole squadron coming at you, and you'd see one dot. That's it. It gave no idea of the numbers because they hide their numbers by flying in its wing formation. You can't resolve the targets. It could be 1, it could be 100. So now you have to know about what minimal range can you resolve. And this is the way it works. This part of the pulse where it says tau right here, this is tau, that is what we use here. And here's the way to think about it. They're talking about resolution in range, actual R range, radial range, not horizontal. Horizontal is even tougher, by the way, but in radial range. So if I have a target here and a target here, target 1, target 2, and I know in time, I'm going to freeze time and just show you what the actual power envelope looks like. I would say that if I have something that, here's my on time like this, and this pulse is traveling this way. Do you follow me on this, class? Now, as it's traveling that way, just try to appreciate. From here to here, there's a pulse. When it hits this thing starts reflecting, right? Follow me? Then it keeps going, and it hits this thing, and this thing starts reflecting. But what if there's no gap? In other words, there's no dead time, you might say, between the time this starts reflecting and this starts reflecting. I won't know where the second target is. Does this make sense to you? The only thing I know is where the first target is, and then the rest is garbled. I don't know. So what they do is say this. If you actually take the tau right there, all right, tau times c is the distance that actually it's traveling, right? So if you wanted to think about a snapshot in time, if you look there, this distance, this would be a distance, it would be c times tau. Now what you want to do if you think about this, if this thing's coming this way and it hits it and it starts moving back, all right, this distance right here is called, I'm going to assume we can resolve, so that the pulse just stops here and this pulse starts sending from here. This is called delta R. It's the range resolution. So the range resolution, R sub u, or I mean delta R, this is called the range resolution, is equal to, as you might guess, c times tau is the distance, but then you divide that by 2. And if you go through the motion on this one, I don't have time to. If you go through the motion with this pulse hitting this and start scattering back, if you're at this range or more, you can see part of it coming back, then deadness, then the second pulse coming back. Anything less than it just overlaps. So that's the maximum range resolution. I've got just a second or two. Now I'm going to do a problem for you with radar, and this is out of Wentworth's book, but I want you to just work through this problem, and I'm going to give you some other problems. We'll talk more about this. So if you look at problem 458, Dr. Wentworth says this. He's got a radar that's equal to 2.45 gigahertz. By the way, there's no police radar at that band. Police radars around here at Ka band, they're 33 gigahertz. This is such a low frequency, it would be thrown out. I'm just telling you that, so if you think this is real, I don't know how he created that problem, but this is like long-range radar for navigational radars. He's got this, and he says that he's got a police radar, and he's got a car like this, and the car is coming at this guy, and he gets a frequency shift, an FD here, of 584 hertz, right? Is that right? This is a problem 8.58. 8.58. 484 hertz is the frequency shift. He gives me that as the frequency here, and he tells me that the total round trip time here, delta t, is equal to 667 nanoseconds. Is that right? I believe. Are you looking at it, or I'm just reading it? Yeah, I think that's right. So the first thing he wants to know is determine the distance to the vehicle. All right, how do I get the distance to the vehicle? Well, the speed of light is 3 times 10 to the 8th meters per second, right? How far did how far did this signal travel in 666 nanoseconds? That's the time delay for the pulse. It traveled 2r, right? Correct, class? So I could say that the distance to the target would be 2r. I mean, I should say this. 2r here, right, is traveled in c times delta t, correct? Or r would be c times delta t over 2. So it would be 3 times 10 to the 8th meters per second times delta t, which is 667 times 10 to the minus 9th over 2. And I think that's 30 meters. You can check me out on that if you want to. I believe it is. So that's how far away the target is. Now the next thing he says, how fast is this thing going in meters per second? Remember, he gives us the Doppler shift right here, right? So what is F Doppler? I know you just had this. Doppler shift is equal to 2 over lambda times velocity, right? So if I multiply Doppler shift by lambda and then divide by 2, I should get V. Now to get lambda, I need C over F. So I can say lambda is equal to 3 times 10 to the 8th, right, divided by the frequency, which is 2.45, times 10 to the 9th. That's lambda. Then I got to divide that by 2. And F Doppler was 584. And that would be the velocity. Can anybody tell me what that is? I don't know. That may be 30 meters a second too, and the other is 100. Maybe that's 100 right here. I'm not sure. Anybody? All right, that makes sense. That's 100 meters is the distance. What is this, though? 30 meters per second about? Anybody?
It's 35.8.
Yeah, that sounds right. 35.8 meters per second. And that's just showing you some basic stuff with radar. I didn't get to do the much else. I'll give you some homework. Next time I'll go through a bunch of it, okay? All right. Thank you. Hope this helped. Can you see me after 2? Because I got to teach.